If you've ever taken a physics class, you know the drill. We start with this perfect world of the ideal gas where molecules are just points and they never touch.
Mm,
And then we spend all our time trying to figure out why absolutely nothing in the real world works that way. It's like the ultimate scientific bait and switch.
it really is. And the person who gave us the first crucial answer to bridging that gap from these ideal points to, real stuff was Johannes D. van der Waals.
Right.
We're doing a deep dive into the ideas that got him his 1910 Nobel Prize, focusing on his realization of the continuous state of matter.
And his whole foundational idea, the bedrock of his work, was this concept of continuity. He just refused to believe that a liquid was fundamentally different from a gas.
Exactly. To him, a liquid was just a highly compressed gas, a very, very dense gas, cooled down. The particles are the same, so the rules should be the same.
A conviction, he said, came from reading a treatise by Clausius.
That's right. It sparked the whole idea. So if you accept that continuity, then all you need to do is adjust the simple idealized gas law to account for reality.
Okay, so our mission here is to unpack the two big modifications he made, the famous constants A and B, and then get into why one of them nearly broke his entire theory.
Well, he introduced these two real-world cheats, you could call them. The first one, mutual attraction, which is the constant A, recognizes that real molecules are a bit sticky.
They attract each other.
They attract each other. So as a molecule zips toward the container wall, the others pull it back just a tiny bit. This reduces the pressure we actually measure on the outside.
Okay, that makes perfect sense. The stickier the molecule, the less force it exerts. So what about the second factor, the proper volume, B?
That one's just as intuitive. It's the fact that molecules aren't points. They have physical size. They occupy space, which reduces the volume available for everything else to move around in.
Right. So the system is working with a smaller volume than the container itself. And on the surface, the VDW equation looks so elegant.
It is. But this is where van der Waals' decades-long intellectual struggle really began. That constant B, the proper volume, turned out to be anything but constant.
Oh.
What he found was that for a very, very dilute gas, the excluded volume B was 4 times the actual molecular volume. But as you compress it, that value drops. It can fall to about half that original figure.
Okay, wait, let's unpack that. A foundational part of his universal equation. It changed depending on how much you squeeze the gas.
Yes, and he was completely honest about it. He called the problem of figuring out the law for B's decrease the weak point of his entire theory.
He confessed it obsessed him, right, even in his dream.
He couldn't shake it. And he knew his initial mistake was assuming B was constant when he calculated the critical parameters, the exact point where gas and liquid become indistinguishable.
Because if you assume is constant, the math predicts the critical volume should be exactly 3 times the proper volume, so 3B.
Exactly. But the experimental evidence, especially Sidney Young's fantastic work, showed the numbers didn't match. Not even close.
How far off was it?
The actual critical volume was much less, only about 2.2 times the initial proper volume. That's a 27% error. In a fundamental equation, that's just not going to fly.
Wow.
So that huge discrepancy, especially right near the critical temperature, it forced him towards a new insight in his later work. He was, I'm quoting him, compelled to assume that molecules start to group together temporarily.
And that's where he came up with the term pseudo-association.
That's the one. It's not a chemical bond. It's not chemistry. It's just the normal molecular forces acting very quickly over very short distances. They start behaving like larger temporary clumps as they get ready to become a liquid.
And there's a fascinating little historical footnote here. He later realized this idea was foreshadowed by a comment from Boltzmann.
Yes. Boltzmann had questioned the simple surface force model because molecular attraction drops off so incredibly fast with distance. And that rapid fall-off is the very mechanism that forces these temporary groups to form.
So what does this all mean for us? Van der Waals' long, hard effort gave us more than just an equation. It gave us the insight that this temporary clumping pseudo-association is absolutely key to understanding how real liquids actually behave.
That's the real legacy. He was always, in his own words, quite convinced of the real existence of molecules. He saw them as actual bodies, not just figments of the imagination, and his work really helped cement that idea in the physics community.
We also can't forget his law of corresponding states.
Oh, absolutely. It was instrumental in liquefying really difficult gases like hydrogen and helium, a huge practical achievement.
Right, but it leaves you with a final thought. If this temporary non-chemical clumping is necessary to accurately describe a simple fluid what complex non-chemical forces are at play in the huge aggregates we call bodies or objects in our daily life, that's something for you to mull over.